In the last lecture, we have seen how it is possible to dynamically balance rotating objects which are of large size, and it is not possible to place them on balancing machines. Now, we have seen how disc like objects of large size can be balanced in its own position, that is what we call as field balancing. What in today's lecture we will see that the same technique can be extended to rotor like objects for complete dynamic balancing, keeping the object in its own position. So, here also we keep the rotor in its own position and the instrumentation required will not be very elaborate, but just like in the case of discs. We can connect it to a small device which we call sine wave generator, and we have pickups at the two ends, and of course, we have a dual beam oscilloscope. So, the sine wave generator is connected to one, and the vibration pickups are either connected to this pickup, which we call the near end pickup, near end in the what we mean that it is nearer to the sine wave generator. And this is called the far end, and this is the far end pickup. Now, as before, what we can do, we can rotate the rotor at sufficient speed, so that we get measurable vibrations through the pickups at the near end and far end, and at the same time the sine wave generator produces a reference sine wave. So, the first test is first run and this is the first run is run the rotor at a suitable speed. So that we get measurable vibration, say a suitable speed omega. Then the near end, what we will get here, as we know already, that oscilloscope output will be giving a reference sine wave, and the other one, say near end, will be something like this. and the far end So, this oscilloscope signals what we get tells that this is the phase lead of the near end response or near end sine wave which you get, and this is the far end. So, the near end response we get as N1 vector, and obviously it is the reference is here. Reference vector is nothing but the sine wave generator. So, this will be similarly at the far end, again the reference will be the same, and the vector representing the vibration of the far end is So, let us see again what we have done. It is being rotated at a suitable speed, so that the near end pickup and far end pickup produces reasonably measurable signal. So, the sine wave generator is producing a signal as a reference. Then the vibration of the near end is being measured like this, and the vibration of the far end is given by this. So, all of these are harmonic functions of time, because it is a case of forced vibration, and in all cases the frequency of vibration is matching with the speed of rotation. So, all these signals are of same frequency. Next, what we do? We stop the machine and let us see the near end and far end phases. This is the near end phase, this is the far end phase. What we do? We measure, we have a datum, a reference line marked, and attach a trial mass MT at the near end at a known radius at a known position. This is a datum. When you do that, then and again after attaching this trial mass at the near end phase, of course, you have to keep in mind that these are also the chosen planes for putting our balancing masses, or taking out material just diametrically opposite location of the balanced mass or balancing mass, as I have said in the previous lecture. Now, if we run the rotor at the same speed and then again we measure the vibration of the near end and far end, what we get now? Now, what we will find that the effect of this trial mass which we place at the near end will be obviously more at the near end vibration. So, what we will have now? The vibration of the near end is now N2. And this is the reference as before. So, this angle is the lead angle of the wave which is found in the oscilloscope with respect to the reference sine wave signal. Now, when we did not attach the trial mass, the vibration of the near end was this. So, this vector this represents the effect of on near end vibration. So, this is the original vibration without any trial mass MTN. This is the vibration of the near end with the trial mass. So, obviously, this difference is the effect of the trial mass only. Similarly, the vibration measured at the other end, that is the far end, will be something like this. So, the original vibration without MTN was F1. So, therefore, this extra, the increase, that is F2 minus F1, that represents the effect of MTN on far end vibration. Remember, these vectors are all rotating like rigid body with the same speed as this, and real quantity is the component along this, which represents, that means, this is the way we represent a harmonically varying quantity. Okay. Next, what we do? We take out this MTN, remove it, and put another mass and we call that mass as MTF at again another known radius or known radial distance at a known position. From a datum drawn on this. Then again we run at the same speed, and the vibration at the near end and far ends are again measured both in amplitude and in phase. Then what we get? So, we must complete also this second run. We have already completed. Attach a trial mass at the near end at a known radius and at a known angular position given by phi t phi m t n. Then the third run at omega. Third run is remove MTN and attach, I have not mentioned because place is not there, attach MTN to the near end. To the far end at a known radius and angular position phi m t f run at omega. So, now we again measure and we get N3. So, if this is the vibration at the near end without any attached mass, then this must be the effect of MTF on the near end vibration. Similarly, at the far end, the vibration is measured and we may get the far end vibration F3. The original one was this without anything. So, this F3 minus F1, this must be the effect of MTF on far end vibration. Okay. So, now let us see what we can do after this. What we have to do ultimately, we have to place balancing masses like say M B N and M B F. So, how you do it? Now, you have to remember that once this MTN is changed to this MBN and MTF is changed to MBF, then when both are placed there, the total vibration at the near end and far end should be 0. That is the effect of MBN on near end vibration and far end vibration plus effect of MBF on near end vibration and far end vibration. When you sum total, the near end vibration should be just minus N1 to cancel the original effect when no mass was attached, and the total effect here on the far end should be minus F1 to cancel the effect of the original unbalance present in the rotor. Now, we have seen in the previous class that how we represent these vector quantities. So, we will use that. What we will do? We will have two vector operators alpha, which is equal to alpha e to the power I phi alpha, and beta equal to beta e to the power I phi beta. Now, when two vectors like A is represented by A e to the power I phi A and B is equal to B e to the power I phi B. When you multiply these two vectors, then what we get? We get a vector whose magnitude is the product of the two magnitudes and their phase is given by the sum. So, if we remember this, then let us see that what we have to find out, that m b n, if we represent by a vector, because it has a magnitude and it has an angular position, that is direction, which is equal to alpha operated upon m t n. Trial mass position is known. So, if I know alpha, then I multiply m t n by alpha to get m b n, and then we will get, this will be alpha m t n, the magnitude will be the product and phase or angular location will be shifted by similarly, the balancing mass at the far end can be written as a product of beta with m t f, that is also can represented by a complex quantity or a vector, because that also has a magnitude and direction. This will be then beta m t f, that will be the magnitude, so if we can find out alpha and beta, that means we find out the quantity alpha and phi alpha and quantity beta and phi beta, then we can find out the magnitude and position of the balancing masses. But what is the condition? Condition is that when this is placed simultaneously, total effect at the near end should be minus n 1 and total effect on the far end should be minus f 1. So, let us see how we represent it mathematically. So, what is the effect of m t n at the near end? This one. So, what will be the effect of alpha into m t n at the near end? It will be alpha vector this is the effect of m b n at the near end, plus what will be the effect of m b f at the near end? It will be beta into what is the effect of far end at the near end? It is f 3 So, this will be the effect of m b f at the near end, and this total should be minus n 1, which was originally present. So, when everything is together, it is 0. Similarly, what will be the effect of m b n at the far end? It will be alpha into and the effect of m b f at the far end this will be effect of, we are doing the far end, this is effect of sorry, we made a mistake, effect of this is the effect of m t n at the near end. So, effect of alpha m t n will be alpha into this, effect of MTF at the near end is this. So, effect of beta MTF will be this, and that total must be this. Similarly, here this is the effect of MTN at the far end. So, effect of alpha MTN at the far end will be alpha into this. Effect of MTF at the far end is this. So, effect of beta MTF, that is MBF, will be this, and this has to be minus F1. So, we get now N21 minus N1, N2 minus N1, N3 minus N1, all these things can be graphically found out. Then only thing what we have to do, we have to solve this simultaneous equation. So, what we do, we multiply this by F3 minus F1. So, we get alpha into plus beta similarly beta or alpha, we multiply this one by N3 minus N1. This is the standard thing. So, we subtract this or change the sign and add, whatever you may say. So, what we get, alpha N2 minus N1 into F3 minus F1 minus N3 minus N1 into F2 minus F1. This cancels, is equal to F1 into N3 minus N1 minus N1 into F3 minus F1. So, finally, we get alpha vector as similarly, we will find out beta also, and which will be, in this case of course, you have to multiply this by N2 minus N1 and this by F2 minus F1, and then subtracting one from another, we will get I think this is just solving simultaneous equation. So, what ultimately solving these quantities by graphical construction will give you alpha e to the power I phi alpha. This will be beta. So, at the near end, this is the reference or datum. Our near end trial mass was here, at a known angle. What we have to do? We have to change this product as, and you have to place it, you have to shift it by this, and this is equal to nothing but alpha, if you keep the radius same, of course, because it is actually the product of the eccentricity and the mass which is important, but just to make the writing less complicated, we are assuming that they are all placed at the same radial direction distance. So, that is missing here, but otherwise you can all the time keep the product of the two as the real quantity. At the far end, if this is the original trial mass you have kept, then we have to shift it to this position, what it will be, which is same as beta into MTF, and its distance angular position will be phi beta. So, therefore, you can see that even a rotor can be, if it is too big, then it is not necessary to bring it to a machine, and it can be balanced in its own location. Now, this particular method which I have shown, where we have used a sine wave generator and vibration pickup and a double beam oscilloscope, I think as we have mentioned in the case of disc like objects, here also you can solve the problem of field balancing using only a vibration meter, which will give you the amplitude of vibration. But in that case, we have to again put each trial mass diametrically opposite position and also at right angles, as we have done in case of single plane balancing, that is a disc balancing, and then we will have many more readings and the computation will be far more complicated, but you can yourself figure out the procedure how we can have or determine the position of the MBN and MBF for complete balancing using only a vibration meter. The other last thing which I would like to mention briefly is that so far we have considered these balancing problems where all these objects or the bodies were perfectly rigid, but in actual practical situation it may happen that a rotor may not be perfectly rigid and it may have some significant amount of deflection or elastic deformation. In such cases, these methods will not work. For that, we have to follow a methodology which we call as the nodal balancing. So, that method is more complicated, more involved, and we will not discuss it here, but I just wanted to mention it so that you are aware of the problem. The other kind of rotary balancing problem is where the mass and geometry of the rotating object is not a very definite one, as you find in case of washing machines, where we put all the wet cloth whose geometry or shape or mass, they are all uncertain. In such cases, a suitable technique is used for self balancing of the rotating objects. That is also another very interesting technique of balancing rotating objects. But I think we will stop discussion on rotary balancing here, and from the next lecture we will take up the problems of balancing machines, where I think the systems involve reciprocating objects.